So good morning, good afternoon, and good evening, everyone. I would like to welcome you all to the Amatech Scientific Instruments webinar series. And today's topic is exploring the nanoscale, scanning electrochemical microscope SECM in action. My name is Aman Bhardwaj, and I am the application specialist based out of Germany, responsible for the Europe, Middle East, and Africa region. Along with me is Dr. Yang Song, our application specialist and the product manager for VersaScan Scanning Electrochemical System, joining us from Oak Ridge, USA. And finally, we have our very special guest speaker, Professor Andreas Lesch from the Department of Industrial Chemistry, University of Bologna, Italy. Here is the table of content that we will go through today. We will begin with an overview of Amatech, introduction to the localized electrochemical measurements, SECM and its standard techniques, and a few published applications. Further, Dr. Yang will take us from AC SECM, constant distance SECM, and their unique applications with a live demonstration of the technique. Finally, we will hear from Professor Andreas about his experiences with the SECM and more specifically, the soft stylus SECM probe and their use cases. If you have any questions throughout the webinar, feel free to post them in the chat or QA sections. We will be addressing them at the end of the session. Amatech is a global manufacturer of high technology product, and we serve a diverse set of niche market and applications. We are more than 19,000 employees working across 150 operating locations across the globe. So now let us begin with an introduction to the localized electrochemical measurements. The requirements of the localized electrochemical techniques originates from the limitations of the bulk electrochemistry, which is predominantly the averaging of signal recorded through electrochemically inhomogeneous surfaces. Therefore, in bulk electrochemistry, localized catalytic hotspots are not located. Surface inhomogeneities cannot be studied, and the microstructural effects are lost. Secondly, in bulk electrochemistry, there is also a limitation to the mechanistic resolution, due to which multi-step reactions cannot be resolved, and mechanistic details are lost. Finally, the sensitivity to mass transport effects causes obscure intrinsic reaction kinetics and complicate the data interpretations, especially in systems overlapping diffusion layers. After all, each electron is identical, and with bulk electrochemistry, one cannot identify where it was generated from. On the other hand, localized electrochemical measurements typically refers to the techniques that probe electrochemical behavior at specific small regions of an electrode surface, often at the micro or nano scale, rather than averaging the response over the entire surface, such as in bulk electrochemistry. In these measurement, probes are typically in 100 micrometer vicinity of the sample. The contrasting difference between the bulk and localized measurements can be related to the various aspects, such as spatial resolution, which is significantly high in case of localized measurements compared to the bulk, or the mechanistic insights, which are better in localized measurements that help detecting the intermediate or local kinetics. These complex mechanisms are often masked in bulk electrochemistry. Out of various type of localized electrochemical techniques, SECM is a type of scanning probe microscopy that uses an ultra micro electrode as a probe. The probe scans close to a sample surface in an electrolyte solution, measuring the Faraday currents from the redox reactions. This technique offers some unique advantages such as versatility, high spatial resolution, and the ability to image the concentration gradient. The electrochemical sensitivity of SECM is affected by the probe size and precision of the measurement electronic devices. Here is an example of how cyclic voltammetry looks like on a macro and a micro electrode. On macroelectrode, that is an example of bulk electrochemistry, CV curves show a typical oxidation peak at 0.2 volt and fall of current afterwards due to the diffusion polarization. What does that mean? It basically means that the rate of oxidation reaction at the electrode becomes higher than the rate of diffusion of ionic species which can participate in the reaction, and therefore it causes a fall of current. On the other hand, it is not evident on a microelectrode because the electrode area is very small and there are always enough ionic species present in its vicinity to participate in the reaction. Therefore, we observe a plateau of current. Generally, SECM experiments are classified in two major categories: scanning experiments and stationary experiments. Stationary experiments are those in which the microelectrode is not moving while one measures a single point electrochemical measurements. On the other hand, scanning experiments are those in which microelectrode moves along the electrochemical measurement, and therefore usually it is regarded as practical localized measurements. In the scanning experiment mode, feedback mode is the most common one, in which sample is not polarized and the SECM tip behaves as working electrode. A redox mediator such as ferricyanide is introduced in the solution, which can participate in the oxidation reduction cycles when the probe approaches a conductor sample. On the other hand, when this probe is approaching an insulator, ionic flux to the electrode tip is limited, and this could limit the reaction and the associated current generated at the tip. With the approach curve experiment in a feedback mode, the goal is to achieve an optimum position of the probe in Z direction, which is appropriately close to the sample. Now let us consider an SECM tip which is reducing iron 3 plus to iron 2 plus while approaching a conductor. In the near vicinity of conductor, the reduced iron 2 plus could donate the electron to the conductor and reoxidize itself to iron 3 plus. This reoxidation causes an increase in the local concentration of iron 3 plus present near the electrode tip, which can again participate in the reduction reaction at the tip. Due to this reduction oxidation cycle, an increase in the reduction current is observed. Of course, a balancing reaction also occurs at the sample outside the local imaging zone during this process. On the other hand, when an SECM tip, which is reducing iron 3 plus to iron 2 plus, approaches an insulator, the ionic flux of Fe3 plus ion to the electrode tip is gradually reduced due to the hindered diffusion. This limited influx of ion limits the reduction reaction and decreases the associated reduction current generated at the tip. Now, when we overlap the positive and the negative feedback curves on top of each other, we get to locate the local imaging zone. This helps us identify how much we need to travel closer to the sample before we can perform a line or area scan in the XY plane. And once the probe is positioned appropriately closer to the sample surface, we can perform an XY area scan. Here we have an area scan where we measured a gold disc sample situated in the center of an insulating resin. The area of the measurement is 2 millimeter by 2 millimeter with a scan rate of 20 micrometer per second. And the probe size is 25 micrometer. Electrolyte is 0.1 molar potassium chloride solution in the water, and 1 millimole of potassium ferricyanate was used as the mediator. The measurements are performed by our VersaScan SECM system. Different from the feedback mode, in generator collector mode, where the sample is also polarized, one electrode generates a redox active species while the other can collect it, often called the substrate generation tip collection or the tip generation substrate collection mode. These modes enable spatially resolved studies of surface reactivity, catalysis, or biochemical activity, offering more direct insights than the feedback mode. Now here are a few of examples of different fields and application areas of SECM. A few of fundamental research areas are the studies of heterogeneous and homogeneous reaction kinetics, electrode-electrolyte interfaces, or the liquid-liquid interfaces. Some applied research areas are in the field of corrosion, electrocatalysis, batteries, sensors, and the biomedical research. Now we will be sharing a few applications for SECM where our VersaScan SECM system was adopted. Here we have a use case in the field of corrosion. Professor Kumar and his research group from India has investigated the nickel-containing carbon nanomaterials that can release toxic nickel 2 plus ions under the physiological conditions. This study uses in situ scanning electrochemical microscope to visualize and quantify this release at open circuit potential. The released nickel 2 plus ions react with ferricyanide to form nickel hexacyanoferrate called NiHCF, which is electroactive and detectable by SECM. Using the redox competition and tip substrate mode, researchers mapped the localized ion release and NiHCF formation. The resulting NiHCF also showed strong electrocatalytic activity towards thiols, suggesting potential biosensing applications. This work highlights both the environmental risk and functional opportunities of nickel-based nanomaterials by mapping the corrosion vulnerable hotspot by SECM measurement. In another use case, researchers from the Vilnius University, Lithuania have used SECM for the electrocatalysis research. Here, femtosecond laser ablation was used to create highly structured copper surfaces with increased surface area. These laser textured substrates were then coated with molybdenum disulfide, forming an efficient electrocatalyst for the hydrogen evolution reaction. The SECM confirmed the uniform catalytic activity across the surface, while electrochemical impedance spectroscopy revealed an enhancement of the double layer capacitance. This study demonstrates how laser structured surfaces can be significantly enhancing or boosting the HER efficiency by improving the catalyst dispersion and surface reactivity, and how the local behavior of electrocatalysts could be mapped via SECM technique. SECM also has a great potential in the biomedical research. Interleukin 6, IL-6, is a key biomarker in oral cancer progression. In this study, researchers from National Chiao Tung University, Taiwan used SECM to map IL-6 distribution in tissue sections from different cancer stages. SECM provided high-resolution label-free imaging, revealing significantly higher IL-6 expressions in cancerous tissues compared to the normal one. This spatial mapping approach enhances early diagnosis and staging of oral cancer. Additionally, IL-6 detection has broader implications, including early prediction of severe COVID-19 outcomes. The study demonstrates SECM's potential as a powerful diagnostic tool in both oncology and inflammatory diseases monitoring. With that, now I would like to hand over the presentation to my colleague Dr. Yang Song, joining us from Oak Ridge, USA. Over to you, Yang.
Good afternoon, good morning, and good evening. My name is Yang Song. I'm the product manager of Amatec VersaScan system. Thanks Among for all the detailed information about the classic SECM technique. Now I'd like to introduce the advanced techniques that developed from the classic SECM techniques. The first one is the alternating current scanning electrochemical microscope, the AC-SECM. SECM is initially and well applied with DC measurements to explore the localized electrochemical properties of sample. Well, it can also be coupled with electrochemical impedance spectroscopy method, so as the ACSECM suggested, to extend our research. With ACSECM, the modulated sine waves will apply to the SECM probe to indirectly measure the localized impedance response of the sample under study. ACS-ECM can be performed to map local impedance at a single frequency or sweeping with a AC frequency range. The probe can also be held stationary to allow the measurement at individual spot for the individual EIS spectrum. Different from DC SECM, ACS SECM doesn't require any mediator. The modulated AC signal, either voltage or current, will apply to the probe. The localized EIS will depends on the solution conductivity, sample's local conductivity, and the applied frequency or range. More importantly, from the result, we can obtain the mapping of the local properties. Like the DC SECM, we need approaching curves to ensure the probe tip is in the local imaging zone. Furthermore, we will figure out the proper AC frequency or range towards the optimized AC SECM scan results. Different from the DC SECM, the AC SECM response depends upon the local conductivity and frequency as well as solution conductivity. To further discuss the dependencies, let's dive into what happened when we apply an AC signal to the SECM probe. To simplify the condition, I'd like to use the potential static ES with a 2-electrode configuration and then without any DC bias as the example. Thinking about if the substrate is absent, once apply the AC voltage to the working electrode at open circuit voltage, the AC current SO will only from the electrolyte between the working and counter electrode, plus the Faradic impedance and the double layer capacitance of the probe. So we can present as the equivalent circuit with RP, the solution resistance, plus the RC circuit for the probe. Once we bring the probe tip near the substrate, similar to the DC SECM, part of the AC response will also from the substrate at the I sub. Once the probe just hands over the sample surface, the I sub would come from both right under the tip and some area nearby. Therefore, we can modify the equivalent circuit with the parallel components for first the solution resistance between the substrate and the probe as the RSP, and then the ones between the substrate and the counter electrode as the RS. Then the associated Faradic resistance and double layer capacitance from the substrate right behind the tip, as shown in the green circle, and the ones from the nearby area that in the red circle. Importantly, once the tip is very close to the substrate within the local imaging zone, as we learned from the DCS ECM, the current from the nearby area would be small enough to be ignored, and the resistance to the counter electrode would be also ignorable since the large surface area of counter electrode. Therefore, we can further improve the equivalent circuits. As shown here, we can focus on the solution resistance between the probe and the counter electrode, SRP, and the impedance from the local zone of the substrate that right under the probe tip. Now we can say once we bring the tip down into the local imaging zone, the AC response would reflect the local property of the sample. Let's move further with approaching curves. Once we do the approaching towards the insulator, we can remove the components associated with the substrate since there's no response from that. Then, with the updated equivalent circuit, we can know that the overall impedance will increase as the probe getting close to the insulative substrate. Since the RP is a major contributor to the overall impedance, the overall results towards the insulator is less dependence to the frequency. More interesting, the AC response towards conductive substrates will be related to the frequency we choose and the conductivity of the electrolyte. As shown in the equivalent circuit, according to the basics of the ES, with lower frequency range, the overall impedance would be majorly contributed from resistors, as shown in the green rod. While the high frequency range, the overall impedance would come from the capacitor components following the red pathway. Therefore, the approaching curve towards the conductor will show dependence to frequency and electrolyte conductivity that relate to the concentration. Within low frequency range, the high concentration solution, as in the green pathway, the solution resistance between the probe and counter elect, shown as RP, will be the major contributor. And the overall impedance will increase as RP increase, as shown in the green curve. On the other hand, with higher frequency range and less conductive solution, the resistance between the probe and substrate will be the significant change upon the distance. So the overall impedance will decrease dramatically once the probe lowered into the local imaging zone near the conductive sample, as shown in the red curve. Again, the AC response from the SECM probe once approaching to the sample are summarized here. Therefore, to identify the localized zone as well as the working distance of the probe tip from the sample, we need the approaching curves towards a selected frequency range. Also, we have the electrolyte conductivity or concentration as another option to optimize the result conditions. Here are some examples of the approaching curves with the standard example of the gold disc we showed before. The gold disc is sealed with epoxy, which is inductor. The Z-line AC SECM experiment is detailed on the left panel. A frequency range of 100 Hz to 1 Hz was applied to each step towards the sample surface. As the data points shown in red, the approaching towards the insulative epoxy just slightly increased, while the green dots from the gold disc are very different. The approaching towards the gold disc gave frequency dependency response from high frequency and low frequency. That's well aligned with our previous discussion. The impedance decreased at 1 Hz, but increased at 100 Hz once the probe tip got very close to the sample surface in the local zone. Therefore, with the approaching curves, we can ensure the local imaging zone and the working distance as shown in the blue shadow. Once the working distance was determined from the approaching curves, We can now lower the probe accordingly, as shown here. The X-line scan was carried out as a confirmation, and then a XY area mapping can be conducted. You can see the impedance difference from the sample surface in 3D model with details from the surface and the edge. The ACS ECM will be a powerful tool to research and applications in sample topological studies, the localized electrochemical activity mapping for corrosion and coating studies. The results on the right is from the publication on corrosion study. The magnesium surface was studied within 0.1 molar sodium sulfate after 2-hour corrosion. The AC SECM mapping shows the local property from the test. Stylus SECM is another advanced alternative SECM techniques I'd love to introduce to you. Different from the classic SECM probe that made from glass and metallic electrode, the Stylus SECM utilizes a flexible probe body with flexible electrode to achieve tasks that classic SECM can never do, especially when we need SECM with delicate biomedical samples. As we discussed, for both the DC and AC SECM, we need to bring the probe tip very close to the sample surface into the local imaging zone. Although the working distance depends on the size of the probe tip, the typical value would be similar or smaller than 100 micrometer. As shown in the schematic, considering the construction of the classic SECM probe that's from glass and metal, the most obvious challenge of the classic SECM will be uneven surface. Even with a relatively smooth sample, we need to ensure the sample will be mounted perfectly level to avoid damage to the probe or the sample. Even the sample surface is uniform enough, we may need to apply a relatively large working distance for mapping, since the result of the classic SECM highly depends on the probe sample distance. The closer to the sample, actually, the more significant of the local enhancement you will see. In addition, inconsistent distance from the uneven sample surface will lead to distorted electrochemical signals and then reduce the spatial resolution. Now let's see how the Stylus SECM to overcome those challenges. As a unique variety of SECM probe, instead of making from glass and metal electrode, we use a flexible polymer body and build a flexible carbon electrode inside. You can find more details from the intersection. On top, we put a very uniform insulator layer as the coating. On the right-hand side, you can see the operation is different from classic SECM measurements as well. Thanks to the flexibility, the soft probe will continuously but gently touch the sample surface with the angle, which typically 40 to 50 degrees. The similar enhancement of current shows in the approaching curves. While slightly different from the classic SECM, the final current with the soft probe approaching to the insulator will remain consistent. This is because the consistent non-zero distance to the sample from the contact angle. As we zoom in into the point where the probe contacts with the sample surface. The working distance between the carbon electrode and the sample can be calculated from the thickness of the insulator coating, which is L, and the angle of the probe, which is theta, as D equals to L multiplied by the cosine theta. Since continuous gentle contact with the flexible probe, the height from the soft SECM probe tip to rough sample surface can be much smaller and well maintained. As shown in the schematic of the comparison as an example, the distance maintains under 20 micrometer within 2 micrometer difference with the soft probe, rather than the significant changes within the classic SECM probes at the same spots. So please mind that with classic SECM method, there's a great risk of damage the probe or the sample from crash. To further ensure the gentle touch, we even slide down the soft probe tip with a desired angle at the beginning. Therefore, to ensure every probe touch on any delicate sample is as gentle as possible. As shown in the demonstration video with the standard gold disc sample, the gold disc is at the center that's surrounded by the insulator epoxy as shown in the insert. Let's start the video. So the initial approach is with a set angle to make sure the soft initial touch. Once the system is ready to measure, so right now it's getting ready, the soft probe will start to continuously slide through a line. And then the probe will always contact with the sample surface gently. So the scan rate can be set it faster or slower, depends on your sample or your preference. So the probe will be lifted with the same set angle and then travel back to the initial position for the next line to finish, and then it will be scanned line by line to finish the XY area. So I really just increased the replay speed. So make sure it's not covered so much time. So I think we can move to see the mapping results. Yeah. So this is the mapping results from the test showing in the video. And also you can see the 3D model from the data. Now I think it's the time that we can shift the gear and take a close look at the Stylus SECM setup with our scan system and software as a live demo. Let me share my screen. All right. So as you can see, I have the setup in my lab. So this is the scan system. And then now the soft probe, the Stylus soft probe holder is over here. So with the holder, you can precisely set the angle from and then you can use the holder to fine tune the angle to ensure the tip of the soft probe will be contact with the sample. So now you can see we are using classic 3-electrode configuration. The probe is a working electrode, and then we have the silver chloride reference electrode, and then a PT wire as counter electrode. And the electrolyte here we use is a 0.1 molar KCl with 1 millimolar methanol ferrocene as the mediator. So I have already bring down the probe, and now the probe is gently touching the sample. The sample showing here is still the standard gold disc sample. So in the center is the gold disc, and it's surrounded by the insulative epoxy. Now let's go to the software. Because the XY area scan will take some time, so I will just show you the X line as a confirmation, also the example how the SoftPro will works. So now we are using the X line, but you can have other selections, the X line, Y line, and Z line for approaching, and the area scan as well. So we will scan from 0 to 1.5 millimeter, 1,500 micrometer with 50 micrometer steps. We'll apply a constant potential to the probe for the scan. So let's do the scan. So let's switch to. So the system is getting ready. Because it's already approached with the step mode, it will remain there until the scan started. So now it's on the insulator area. As you can see, the current is going down and then relatively lower, as we expected from the insulative surface. So once the probe is approaching and reach the conductive, you can see the enhancement very obviously. And the current is very stable, but with a small difference that's showing like the slightly different properties from the sample, maybe just scratches. So once it's done, the probe will be lifted up with an angle. So, and then gently bring back on the surface with a very gentle touch. So the data can be exported and then can be reproduced with other third-party tools if you need it. Okay, so next, please welcome Professor Andrew Lesh at University of Bologna to introduce the most advanced researchers with the status SECM techniques. So, Professor,
yes,
the stage is yours.
Thank you. Yeah, good afternoon or good morning, good evening to everyone. Thank you, Yang and Aman, for the technical introduction. Thanks for the organizers of this webinar to invite me as a guest speaker. And yeah, it's my pleasure to present you some of the application highlights of the recent years of using soft stylus probe scanning electrochemical microscopy. Just very few words. How did I get involved in the successful story of soft probe SECM? Over 15 years ago, Professor Hubert Giraud from the EPFL in Switzerland asked to Professor Gunter Witscher from the University of Oldenburg in Germany, why not simply use soft probes in contact mode to maintain a constant working distance for SECM? And being convinced about this new approach, they got funded a binational project over several years, and I was one of the lucky PhD candidates that were involved from the beginning in the development of the soft stylus probes. Worked on that also after a PhD as a postdoc researcher, and since 2018 as a professor of analytical chemistry in the Department of Industrial Chemistry at the University of Bologna. However, many other researchers, professors, and students have been involved over the years, and there's no space to acknowledge all of them, but you will find them in her names, you will find in the cited publications of the following slides. So, starting with some challenging substrates that have been investigated with soft probe SECM, we start with some rigid samples that are also quite large. So as you can see from the scan dimensions, we are talking about centimeters. That is extremely challenging with standard SECM using a hard tip without any distance electronic control. But this metallic pin with some insulated local features representing letters has been scanned with a simple horizontal movement using the soft probe. And using SECM feedback mode imaging, it was possible to demonstrate very clearly the conductive and insulating parts of this surface that contains surface features of several tenths of micrometers over a distance of centimeters. I repeat, that is extremely challenging to do with the standard SECM, where all the response will be superimposed by topographic artifacts and not by the reactivity of the substrate. With the soft probe here, we see only surface reactivity independent of the surface topography. So the soft probe follows the macroscopic topography of the sample. It can also be done with quite extreme samples like curved structures, where the surface is coated with conductive and insulating stripes. Doing on this curved substrate of several hundreds of micrometers side difference SECM feedback mode imaging resolves very clearly the conductive and insulating parts. Again, with the standard SECM with horizontal probe movement using a hard tip, you won't see these structures, as everything will be superimposed by topography. However, as already also mentioned by Jan, with these soft probes, we have further advantages. The pressure that is exerted on the surface is extremely low, so they can be used also for mechanically fragile or delicate surfaces, like self-assembled monolayers printed on conductive substrates, tissue samples. Here we go in the direction of biomedical applications, even single cell cultures are principally able to be analyzed by using the soft probes, brushing very gently over the cells. Where the video is not going. Okay, but here in this case, we also have scanned other kinds of biological samples, such as the peel of an apple. And I apologize that the video is not going, but here we would see that the soft probe is following exactly the topography of this apple peel. And this work, we studied the antioxidant activity of the apple peel. Going a bit more into detail to demonstrate the key advantages of the soft probes, we see now some SECM analysis of self-assembled monolayer structures that were micro-contact printed on a gold surface. More precisely, it was structure of hexadecane tile, where hexadecane tile was printed on the gold surface. We will see a reduced regeneration of the redox mediator in SECM feedback mode. We will see a high response on the uncovered gold surface. So doing SECM imaging will show high currents over bare gold and low currents over the self-assembled monolayer structures. We did, with the soft probe in contact mode, a first image of an area of 2 by 2 square millimeters. We repeated the measurement using a slightly larger area that was including the same area as the first experiment. So brushing over the surface was here repeated, and the image in this part is exactly the same as before, demonstrating that the contact mode scanning with this soft probe did not cause any damage to this very delicate self-assembled monolayer structure. And estimating the pressure that we exert on the surface, we can state that this pressure is several orders of magnitude lower than, for example, for AFM tips. Demonstrating how delicate these self-assembled monolayers are, what we did was scratching the self-assembled monolayer with an Eppendorf tube tip, did imaging again, and it showed clearly the removal. So demonstrating again the low pressure that we exert on the sample surface using the soft probes in contact mode. Then going to some more biological samples of interest, we were analyzing tissue sections. Here an example of a mouse heart tissue section, where we used SECM feedback mode imaging using ferrocene methanol as the redox mediator to demonstrate the distribution and concentration of hemoglobin. Where the current were increased, there was a higher concentration of hemoglobin. And also here in this case, the sample area is extremely large for SECM standards. And this was possible thanks to the use of the soft probes. Another important advantage of using the soft probes can be seen in this scheme here on the right. So we use a certain probe angle that helps mechanically to stabilize the contact mode scanning and to keep the soft probe in contact with the substrate. But there is another advantage. Due to the inclination of the probe, the active part, so the carbon microelectrode, will never be physically directly in contact with the sample. So there is no risk of microelectrode contamination, and it keeps the constant working distance for the flux of the redox species that are necessary for SECM imaging. The constant contact is also important for biological samples because over time, in solution, they can swell, so they can change a bit the topography, which using the soft probes is not an issue anymore. Being a bit more precise with applications, we were working on melanoma. Melanoma is when it is not identified at superficial stages where it's still curable, a quite deadly cancer. So it is very important to identify it at early stages by discriminating melanoma from a harmless normal skin mole. Even if nowadays optical microscopy has advanced for the diagnostics of melanoma, the gold standard is and will also be for a long time to do an invasive procedure, which is skin biopsy, removing skin and slicing it into tiny tissues that are arranged as an array. Then you do immunohistochemistry, that is coloring the distribution of certain melanoma diagnostic markers. However, as all optical methods, they can be influenced, interfered by optical interferences. This is a problem that we do not have with electrochemistry, where we're not based on light. So what we did was we selected one of the diagnostic melanoma markers. In our case, it was the protein tyrosinase. We labeled it with a primary antibody, sensitive and selective for this biomarker. We used secondary antibody conjugated with a peroxidase, adding in the electrolyte solution substrate for the peroxidase and hydrogen peroxide, caused the oxidation of this species that was then detected by the SECM probe. So in this case, we also show the example of the sample generation tip collection mode of using soft stylus probe SECM. We were able to image by using SECM imaging the distribution of this diagnostic melanoma biomarker without optical interference and compared it with the conventional immunohistochemistry. What we can get out from these SECM images, we can then analyze the data. We can, for each tissue slice, take the mean current as the global signal of this specimen to express the tyrosinase overexpression, to do a staging of the melanoma between stage 2, stage 3, or let's say normal skin. And then we can use the standard deviation expressed here by these lines to see the heterogeneity of the distribution. And all these are clear indications used for melanoma staging. And it was possible thanks to the use of the soft probes that got a very stable signal for these important samples using contact mode, non-damaging the sample, and getting a constant working distance. Showing even more the challenges of biological samples, we also analyzed thick tissue sections, so tumor blocks, always in melanoma research. And here, to get a higher topographic resolution of using the soft probes, it's possible with the laser or even with very small blades to cut the cross-section of the soft probe that is in mechanical contact with the substrate into very small dimensions and slide them over this challenging three-dimensional sample. And also here, it was very clear that by contact mode SECM imaging, we have been able to get homogeneous response for the melanoma thick tissue and normal thick tissue and distinguish melanoma from normal skin. The last example that I want to show is the analysis of bacterial biofilms, also a very important specimen in not only for biomedical applications, also for many other fields. And also here, it is a very big advantage that we have always a constant working distance independent of the morphology of the biofilm. The bacterial biofilm is very challenging, can be also a bit gel-like, so it's extremely difficult to do that with a non-soft SECM probe. So here in that case, we used also a mediator like ferrocene methanol and a feedback experiment. And due to the presence of bacterial cells in the biofilm, there can be the reduction of ferrocene methanol plus that is generated at the soft microelectrode in the respiratory electron transport chain of these bacterial cells. So it's a part of the metabolic activity of the bacteria. This oxidized redox mediator replaces oxygen as the final electron acceptor and gets regenerated and causes the regeneration current. So you can determine the reactivity of the biofilm by using this SECM. And what is very important when doing analysis of challenging biological samples like biofilms, you have to do a number of experiments that are statistically relevant. So here we did, for example, approach curves on the biofilm and on the glass as an insulating reference. And we repeated the approach curves, in particular on the biofilm, using different biofilms that were identically grown and on different locations on the biofilm. And as you can see from the responses, there was a very good repeatability of the experiments, which shows again the huge advantage of using the soft probes, even for very challenging specimen. You can also do imaging in a very stable way, as demonstrated here. And what could be possible applications? So you can study the stability, the reactivity, and the growth rate of biofilms under different environmental conditions, for example, but you can also study the antibiotic resistance. However, very often it's not so easy to transfer a biofilm from a real outside sample into the laboratory. So what we have demonstrated is that you can collect these biological samples like biofilms using medical or similar high-quality Scotch tapes, where you collect the biological sample with this adhesive layer. Then you can bring the Scotch tape into your SECM. Okay, and then you can do in electrolyte solution an analysis of the film that you have just collected with your tape. The big advantage of the soft probes is, again, that you have no direct contact of the active part of the soft probe and the substrate surface, no contamination of the electrode. And we have even demonstrated that the adhesive layer does not cause any disturbance for the measurements. So we have made analysis, for example, of the antimicrobial resistance in a very convenient way using these soft probes. So as already mentioned, it's a very powerful tool to study the antimicrobial resistance of biofilms. So to conclude just this part, so the soft stylus probes enable scanning not only of tilted, corrugated, and delicate substrate, but also large areas. So there's a big difference also to the standard SECM. The soft probes adjust their sliding very conveniently to the macroscopic surface morphology of the samples. You can apply all common SECM modes. And it's extremely powerful, but not limited to scanning biological specimen. So thank you very much for your attention.
Thank you very much, Professor Andreas, for all these interesting application examples. So what we have noticed there is that to be able to obtain high quality localized measurements results, we should consider the resolution and accuracy of SECM system. That depends upon several interrelated factors. Positioning system precision ensures the accurate probe placement relative to the sample, and the measurement resolution of current or voltage will affect also the sensitivity to measure the subtle signals. Probe diameter influences the spatial resolution. That means smaller probes would yield finer details but weaker signal. And consistent minimal probe to sample distance is critical for accurate imaging. Also, electrolyte conductivity affects current distribution and signal interpretation, and the optimization of all these parameters is essential for a reliable, high-resolution SECM data. With that said, let's take a look quickly at the instrument behind the science that we saw today. The VersaScan Scanning Electrochemical Workstation. This is a versatile platform that enables all high-resolution, nanoscale electrochemical imaging techniques we have discussed today. Compact, modular, and powerful, it is designed to adapt a wide range of research needs in surface science and electrochemistry. VersaScan supports a suite of advanced scanning probe techniques, each tailored to probe different aspects of surface and interfacial phenomena. SECM is to control and monitor redox reactions with high spatial resolution. SKP measures work function differences in air using a non-contact, non-destructive method. With SWET, one can visualize local currents distribution mapping voltage fields in the solution, and LEIS is used to characterize impedance and phase behavior locally through AC response measurement. OSP can be used to map surface topography optically and integrate that data with electrochemical modes for constant distance mapping. And finally, the SDC performs localized electrochemistry within a precisely controlled droplet environment. Together, these techniques make VersaScan a powerful tool for exploring the nanoscale world from corrosion science to energy materials and beyond.